today I'm presenting my Intelligent Systems and Control course project, which was Fuzzy ANFIS Leader Follower for Mission Control for obstacle aware and obstacle avoidance of swarms of unmanned ground vehicles. This project was made by me, Mohammed Ayman, and my friend who is not here, Fatis Kamil. The presentation outline, it's divided into 4 parts. The first part is the motivation and statement, related work and background. Second part is system architecture and FIS design, state machine and lane behavior. Third part is obstacle aware extension, and the second extension was ANFIS based leader controller. The fourth part is the simulation results and the discussion. Now with the first part, motivation and problem statement. Why swarm information control is hard, but it is important. The motivation behind this project is the importance of swarm. They can be used in search and rescue. They can cover a wide range of area. Surveillance, they can be used in surveillance. They are coordinated UGVs patrol without gaps. They can reach hazardous environments that normal humans cannot reach. The core challenges, swarms, it's hard to maintain inter-robot spacing without collisions. The navigation in cluttered environments is hard. The self-organized from arbitrary initial positions. Also, it's hard to handle sensing noise and modeling uncertainty. Why for mission control becomes difficult? In UGV swarms, we have to satisfy 3 rules. 1, they should stay close enough to the neighboring agent. They should stay far enough to avoid intercollision, and they should bend in the trajectory that the leader makes. Technical contribution, we first reproduced the paper, which was presented in IEEE. So it was a 2D UGV adaptation. Second, we added an obstacle avoidance extension. Third, we replaced the fuzzy controller of the leader with an ANFIS leader replacement. Related work. The background behind this project is swarm robotics, as I said, used in varying industries, including warehouse, entertainment, agriculture, and military. Also, swarm formation enables covering wide range of areas. They are robust and efficiency versus single robot system. Also, fuzzy logic controller makes it easier to tune the gains, but the only gap it has is it needs an expert to tune these gains. And this is a trajectory that the main paper did, and this is the paper that we reproduced. And these are the papers that we used in our project. And the paper limitation, it didn't conclude any sensing noises or collisions. It also didn't say that it's fully safe. It was not scalable. Also, it was hand-tuned. So part 2 is a system architecture and FIS design. It's a 3-layer: the leader, fuzzy inference, the nearest neighbor, and the obstacle. In this section, we try to answer 3 questions. Question 1: is it too far or too close to the leader? The second question is it too far or too close to the neighboring agent? And the third question: is it too close to the obstacle or not? So X1 is the crowding area that the agent should have between it and the leader. And X2 is the distance between the agent itself and the leader. And this is the output. So if it's -1, you should approach. If it's 0, you should hold. If it's 1, you should retreat. The same thing for the nearest neighboring agent. The x1 is the area surrounding the agent. X is the distance between it and the neighboring agent, and this is the strength. If it's -1, so it should approach. If it's 0, you should hold. If it's 1, you should retreat. And this is the obstacle controller. This is the distance between the agent and the obstacle. And this is the equation that we use. V base is the main controller, is the main equation that we use to adjust the distance between it, between the agent and the leader, and the agent and the neighboring agent. V lane. If you have an agent that blocks the way of a leader, it should be pushed away from the leader corridor. Then we move to the next equation, which is the V-tail. So now it's not blocking the way of the leader, but it should be behind the leader. So V-tail is responsible to make this agent to be behind the leader. Okay. V-obstacle, which is responsible to adjust the distance between the agent and the obstacle itself. V-separation. This is an emergency separation to make it like if we are about to have a collision. This is responsible to avoid this collision. V-leader directed recovery. This one is responsible to make if we have an agent that is now very far from the herd. So this equation is responsible to make it catch this herd. V-jet. It's if we had two obstacles and one agent, and the distance between these two obstacles very narrow. So now the agent can reach velocity of 0. So this is a random push to make this a random push towards the leader to make the agent reach the herd to reach the herd again. And this is the membership functions that we use. Now for the fourth part, it's a state machine and lane clearance. This is the trajectory, the pure trajectory we use. First, we have a leader in point A. It should wait and start until there is a ring or we can say it's partly a ring. It's a partly ring of agents. So now, when the ring is complete, it should move to point B, and agents should follow that leader. Now, when the leader arrives to point B, it should wait until the agents make a full ring. Now the trajectory is full, and this phi is a readiness matrix, because we will never have a fully circled ring around the leader. So now I make this equation. It's a fraction equation. This is the tolerance, and we have here 1 over n, 1 over the number of agents, and this is the distance between the leader and the agent, and this is the distance of the diameter of the ring, or the radius of the ring, and this is the tolerance. So now we have 10 agents. The first agent reached the radius of the ring. Okay, so now we will count it 1. The second one reaches the radius of the ring. So now we count it another 1. So it will be 1s and 0s until we reach approximately 0.7, a 0.7 or more. So now it should be now the leader should start moving. And now this is our first extension, which was obstacle avoidance. We divided it into 4. We had 3 Mamdani rules for the obstacle. If it's very close, medium, and far. If it's very close, we should steer away. If it's medium distance, we should avoid it. If it's far, we should ignore it. The scaling. So now we did that because we wanted it to be more realistic. If we have an agent at the very back of the herd, so now it should not do the same thing that all the agents did. So now we can make it, instead of going to the obstacle and avoiding it, it can just be aware of it, and just to make it easier for him to reach the herd again. So this is equation we made to make it easier for it to avoid the obstacle before reaching it. Hard projection, which I said before, it's it's responsible to make it to make a slightly a small push to make it reach the herd again. A jitter escape, this one is responsible if the agent is stuck between two narrow obstacles, we give it a small push to reach the leader. And the second extension was the ANFIS controller. Here we tried to add another thing. We replaced the fuzzy controller with an ANFIS controller to make it data-based. So we collected the data from different scenarios. We used when the number of agents is 15, 30, 40, and all of them we used a random obstacle positions. And we split the data into 70% training and 30% for the validation. Then we trained it. Then we only replaced the leader controller with the ANFIS. We didn't change anything. And this is the simulation result. This is the result. This is for scenario 1 with no obstacle avoidance. This was the trajectory that the leader and the swarms did. This was n equals 25, n equals 40. This is when we used random obstacles. We can control the number of obstacles and the position of the obstacles. And this is the good speed. They didn't make a full ring because the number of agents are not many enough. But here they will make a ring. They are making a circular ring around the leader, and they also trying to maintain the distance between them and the leader, and between them and the neighboring agents. Trajectory. this is the third scenario where we added ANFIS for the leader. This is the
So they are randomly choose the direction, otherwise left or right.
Yeah, randomly. If it's here, it will not take this path. It always takes the shortest path towards the leader. Like if it's here, it will, of course, it will not take this trajectory. It will take the shortest trajectory. Like if the agent is here, okay, and the leader is here, of course it will take the shortest path, which is here. Okay. If the agent is here and the leader is here, of course it will take the shortest path, which is here. Okay. And this is a chronological behavior from a random logic. And this is a strength in our project. It's interpretable. Fuzzy rules provide human readable logic. It's a modular. We added obstacle avoidance, lane clear, and ANFIS. It's a scalable. We used various numbers of followers and various numbers of obstacles. It's data driven when we use ANFIS. But the limitations is we didn't adopt it in our hardware, but it's in our future expansion. We also didn't do it in 3D extension. We didn't add sensors. This is the conclusion. Okay.
Thank you. Any question?
Is my friend? Yeah, I have a question. While they are making obstacle avoidance and following the leader, they are making some sort of path planning within this, or how they are choosing the shortest path?
The shortest path during the obstacle avoidance, yes?
Yes.
Okay. So now, like I said, it's easy. There's no trajectory. There's no path planning. It's just like if it's here, the obstacle is here, and the leader is here. It always measures the distance between it and the leader. So and it also measures the distance between it and the obstacle. So it combines them and it sees where is the shortest path towards the leader. Then it will take it. Okay. Yeah.
Okay, I have a question. For the obstacles, are they fixed or
No.
they're moving?
No. Obstacles are fixed, like this chair or this table.
So they're not moving.
Yeah, but we can change the number of obstacles and their position.
Okay.
We can add.
In case
Mhm.
the leader, let's assume that we have a scenario where a leader hits the obstacle. Are the followers will hit the same, doing the
No,
same
no.
mistake, or
No.
they will just?
That's why in the video you can see that the followers can take another path and they can face another obstacle that the leader didn't face, and they will not hit it.
So the main idea is formation control.
It's formation, yeah.
So when they move from point
Point
A
to
to point B, they have to maintain the formation control. This is the
Yes.
circle at the end.
Yeah. The circle when it's settling, when there is no movement, but they should make an arc behind the leader when the leader is moving. So the shape is differentiate between it. If the leader is not moving, they will make a circular ring around the leader. If the leader is moving, they will make an arc behind the leader.
Because you make it centralized. It is
Yeah.
distributed or centralized will be more
decentralized will be better, because swarms should be decentralized controllers, because one of the extensions that we want to add is, what if the leader is dead? So
Faulty.
yeah, what should happen? In this case, they will die.
Okay, good. Thank you.
Thanks.
Close me.